Welcome back to trigonometry. In this video we're going to talk about some really basic properties of the trig functions we just defined, sine, cosine, and tangent, just to kind of see how they work. And that's always a good idea when you define something new. Do some examples, figure out some really basic things about how it works before you try to do anything too complicated. So first of all, let's talk about notation. Trig functions have a really long and storied past. They were used by the ancient Greeks thousands of years ago, and then a lot by sailors navigating the globe and things like that. So there's a lot of shorthand and special rules that apply to how we write trig functions that you don't always do with other functions. So when you're writing down a trigonometric function, you can write it like a regular function. So if I just have some function f of t, you write f parentheses t, and whatever's inside the parentheses is what you put into the function. And you can do the exact same thing with any trig function. You can write parentheses and put in whatever you want, so like sine of 2 pi. But there's a really common shorthand with trig functions that you don't put in the parentheses. So I could just as easily have written sine of 2 pi, and that would be fine. That doesn't mean you can write a plus or a minus, so that's, if I want to write, say, sine of t plus pi, if I want the t plus pi to go into the sine, then I have to write it like that. I have to put parentheses. So that's not the same as the sine of t plus pi, which would actually be interpreted like this. First you do sine t, and after you plug in t to the sine function, then you add pi. Okay, but when you're just multiplying, it is okay to write parentheses. And the same is true when you're multiplying several trig functions together. So I could also write something like sine of pi cosine of pi over 2, and that's a totally fine statement. It really means like this and like this, but oftentimes we leave off the parentheses. Same with negative signs out front or constants out front. So if I write minus 2 sine t, that's a totally fine thing. I really mean negative 2 times the sine of t, but often we leave off the parentheses. So that's a little bit different from regular functions, but not so different. What's really weird is how we write exponents. So if I want to do something like this, the sine of t squared, you can always choose to write it like that. You can choose to write it like a regular function. Like if I wanted to do some other f of t, I'd have to write f of t squared, and lots of parentheses. But parentheses kind of just mess things up, and you get a lot of them all the time. So we developed some shorthand for this, and what we do is we put the squared after we write sine. So that sine of t in parentheses squared is exactly the same as writing sine with an superscript 2, sine squared t. Okay? So you could also write sine squared t, but you cannot write sine t squared without any parentheses. That's actually equal to the sine of t squared, which is different. So it's not the case that sine t squared is the sine squared of t. Okay, so that's a little weird, but you'll get used to it. So that's just notation. That's not really anything special. What is special about sine and cosine? Well, the first thing is the Pythagorean theorem. I know, I said it's the most important theorem, and it really is. So how does this work? If you put in any angle t, if you square the sine of that angle, square the cosine of that angle, and add them together, you always get 1. So let's look at why this is true. Of course, we're going to use the unit circle because that's where sine and cosine come from. So anything we derive about them, we're going to start by looking at the unit circle. So let's say I have an angle here, t. Then this point, xy, is equal to cosine t comma sine t. Sorry, that's a little cramped on the side there. And remember, the radius of the circle is 1 because it's the unit circle. So if I make a triangle here, this distance is y and this distance is x. And I know from the Pythagorean theorem about triangles that x squared plus y squared equals 1. But x is cosine t, so that's cosine squared t. Remember, that really means cosine of t and then square it. Plus sine squared t is y. Oops, sine squared t is y. So add them together, you get 1. And that's really just with the Pythagorean theorem, except instead of x and y for the sides of the triangle, they're really cosine t and sine t. Okay, so that's our first thing that's really special about cosine t and sine t. There are very few functions where if you square them evaluated at any point, and add them, you get 1. So what else can we say about cosine t and sine t? Well, let's just look at our old friend, the unit circle, and evaluate sine at a few points. So say I'm looking at this point here. This is 1, 0, because we're on the unit circle. We can think about that as what we get if we make an angle of 0 radians with the positive x-axis. So if I look at the sine of 0, well, the y-coordinate of that point there is 0, so the sine of 0 is 0. But what if I go around again? So what if I make an angle of 2 pi radians? Remember, 1 full revolution is 2 pi. I get back to the same point. So I also have that the sine of 2 pi is equal to 0. Okay, well, what if I go around twice? Once, twice. Then I've gone 4 pi radians, and I get back to the same point, so then I have that the sine of 4 pi is equal to 0. What if I go backwards? What if I start here and I go backwards 2 pi radians? I still get 0, because I land at the same point no matter how many times I go around. So it doesn't matter how many revolutions you go to when you're evaluating the sine. All that matters is the point where you end. Okay, so what we're seeing is that the sine of any multiple of 2 pi is equal to 0. And a very similar thing works for cosine. If I look at the cosine of 0, that's going to be 1, because it's the x-coordinate of our point here. Cosine of 2 pi just means I go around again, but I've got back to the exact same point, so that's still 1. If I go backwards and do cosine of negative 2 pi, still going to be 1, because all that matters is the point where I end up. So in fact, this works for any angle. You don't have to have this with angle 0. You can do any angle you want. And what we see is that if you start at some angle t and you rotate by 2 pi, you end up at the same point. So let me draw another circle to illustrate that. So if I have any angle t here, this point is going to be cosine t, sine t. But I could get to that point by doing other things. I could also go all the way around and then go up to t. Or I could go backwards a number of times and then go to t. So it doesn't matter if my t is off by some other angle by any multiple of 2 pi, positive or negative, then I'm going to get the same thing. Okay, so you could even write it in a fancy way, or a less fancy way. You could say, well, the sine of t plus 2 pi is the sine of t plus 4 pi, sine of t plus 6 pi. I think you get the idea. Dot, dot, dot. If you want to be real fancy, you say it equals the sine of t plus 2k pi for any integer k. And that's the super formal way of saying it. And because this is such an awesome phenomenon where if you shift sine by certain values, it repeats itself, we give this a name. Such a function is called periodic. So in general, a function is called periodic with period k if when you put in a number t, you get the same thing as if you would put in a number t plus k. And that has to work for anything that you're allowed to put into the function. Okay, and then we call the function periodic. So what we've seen here is that sine t and cosine t are periodic with period 2 pi. Because if you shift them over by 2 pi, you get the exact same function back. You get the same values for any t you put in. Okay, so that's pretty special. That's actually what makes trigonometry useful, is this periodicity. Because it turns out that just about anything in the real world that behaves periodically, that repeats itself after some amount of time or amount of other stuff that happens, but generally we think of time, anything that repeats itself over time is going to be well described with sines and cosines. And that's really what makes them useful. We don't really care too much about triangles. We care a lot about periodic functions. Okay, so that's pretty awesome. Sine and cosine are periodic. What else can we say about them? Well, one last thing. Let's look at this circle here and draw an angle t. So maybe I'll go in the third quadrant this time. So I have some angle t. Okay, so let's call this x comma y. So cosine t is x. I guess I can write that down. Cosine t is x. Sine t is y. Now what if I go backwards and make the same angle? So what if I go back by an angle of t? That would be angle negative t. then the y coordinates are going to be very similar. One is going to be the opposite of the other, and the x coordinates are going to be the same. So that's going to still have the same coordinate x, but now it's going to be minus y. So that means that the cosine of negative t is going to be the x coordinate of this point down here, but that's still x. So that's still equal to the cosine of t. Cosine does not care if there's a negative sign inside. Cosine of negative t is the same as the cosine of t. You can just forget the negative sign if you want to. Sine is a little more finicky. If you look at the sine of the angle negative t, that's going to be the y coordinate of my point down here, and that's negative y, which is negative the sine of t. So often we think about this as being able to pull out a negative sign from the sine function. So for example, if you want the sine of negative pi over 6, that's just, you can basically pull the negative out in front, and it's negative sine of pi over 6. Okay? If you want to do the same thing with cosine, you just forget the negative. So the cosine of minus pi over 6 is just the cosine of pi over 6. Because when you go opposite directions, you don't change the x values. All you're doing is going down instead of up, or up instead of down, and the x values stay the same. Okay, so those are some really basic special properties of sine and cosine. We'll talk about more of these in class, and of course, throughout the course, we'll develop many, many special properties of sine and cosine. This is just the tip of the iceberg, if you will. So with that, have a good afternoon, and I will see you in class.